All right, so we're going to talk a little bit about radiation. So radiation is the spontaneous emission from particles from the nucleus. Remember, we have three subatomic particles. We have protons, neutrons, and electrons. This area right in here, the protons and neutrons, are the things that we can get rid of from the nucleus. But remember, the neutron has both positive and negative charges, so it acts kind of like a proton fused with an electron. So we start talking about emission of particles from the nucleus. Because the neutron is situated like it is, we have more different types of particles that we can release. Now, radioactive decay is when a nucleus undergoes a change to become a new type of nucleus, and usually a smaller nucleus. And then radioactive stability, we'll talk about. So there are slightly more than 100 naturally occurring atoms on the periodic table. So nuclear instability occurs when the number of protons becomes so large. Because if you think about the nucleus, right, so if we have a bunch of protons in the nucleus, right, and we have neutrons in the nucleus, right, that's a lot of positive charges, and like charges repel each other. Now, because there's a negative charge in the neutron stabilizes the nucleus somewhat. But as we start getting larger and larger, right, that positive charge ends up becoming too much, right, even by the addition of neutrons. So we're going to start needing more and more neutrons to surround this nucleus to make it stable, right? And really, that starts to happen around calcium. So we talk about right here that nuclides with 84 or more protons are unstable, but really the light nucleotides are stable when Z equals A minus E. So if you look at calcium, right, so A in calcium would be 40 and Z is 20, right, and that's 20, right? So right after we get to calcium, then we start getting larger and larger. So if you look at scandium, which is right after calcium, right, then we get 45 minus 21 equals 44. So we have 44 neutrons. So right after calcium, we need more and more neutrons to make it stable. So we said that at 84 or more, so 84 is right here, right? That's polonium, right? That's 84. So you notice the last non-radioactive element, purely non-radioactive element, is probably lead, right? And we have lead right here at 82. And you know that lead they use, oh, sorry, I got off the camera there. So lead they use to shield us from radiation. It's the densest metal we have that is non-radioactive. So lead, but you'll notice right next to it, bismuth is kind of red. So it's kind of bordering on being either radioactive or non-radioactive. So it's a low-level radioactive isotope. But the funny thing about bismuth is pink bismuth. Is Pepto-Bismol, is what they give for upset stomachs, right? Just bordering on being unsafe, right? And then you'll look at other things in here. We have uranium here, right? And uranium is used in nuclear reactors. So you notice that uranium is kind of a reddish color too. So it's fairly stable in its naturally occurring isotope. But when I change it, it becomes very, very unstable. Uranium and plutonium, which is two off of it, are used in making nuclear bombs, right? All right, so the strong nuclear force, right, so this thing, the strong nuclear force, right, is that force that holds the nucleus together, right? I didn't make up the name, they made up the name. It's called the strong nuclear force. And the strong nuclear force is increased with the increasing amount of neutrons. So the ability to hold together depends on the proton-neutron ratio, right? So if you think about what we just talked about, right? Calcium being the last of the small nucleotides. So calcium is right at 20. So if I go 20 and 20, you notice I'm right on that line. But anything above calcium, that red line, that dotted line that deviates, is the amount of neutrons that are available to hold it together. So if you know right up here at the top, mercury, right, is 80, so that's 2 before lead. So if you go right above it, right, we'll get lead and bismuth, and then everything larger than bismuth, there's no stable isotope. It's all radioactive, right? So we usually say that lead, number 82, is the last of the stable, right? So radioactive decay. So these are particles emitted. So those are particles emitted during radiation, right? So let's see what we got here. So we have alpha, right? So alpha production. So alpha particle is what we call a helium core. So this is a helium atom. Without electrons, essentially what it is. Remember, most of the space of an atom is electrons. So they said the size of the nucleus of a helium atom, if you want to give a reference to size, right? If you took a dime and put it in the middle of a football field and put the electrons on the end zone, right? That's the relative size of the center of a helium to its space with electrons orbiting around it, okay? So the helium core is really small. But you'll notice this ends up being a chemical reaction. So the strategy of this is you have to make the products match the numbers of the reactants. So let's take uranium, right? So uranium-238, remember it's got the 92 protons. So if it releases an alpha particle, right? So this is our alpha particle, our helium. Then all we do is we say this number here, the 90 of thorium, is 92 minus 2, because that's what happened here, right? And the top number, right, here is 238 minus 4, right? So that's equal to 234, and this was equal to 90, right? So that's the way we figured this out. So if I said this, so if you look at your periodic tables, get your periodic tables out, right? If we said that we had radon, right, and radon is going to be 222, right, and then 86. So if that emits an alpha particle, so an alpha particle is my helium core, then what I would get is, right, so I would do 22 minus 4, right, and so I get 218. Oops, that's not 218, that's 281. I get 86 minus 2, that would be 84. Then I'd look at my periodic table, right, and 84 would be polonium, right? And that's the way we do it, right? So the numbers on the product have to equal the numbers on the reactant, right? So alpha, and then we have beta. So we'll come right over to beta production as well, right? So beta consists of a high-speed electron. So we got, this is our beta right here. So really it's a high-speed electron. So you'll notice that the mass of an electron is relatively zero. So the mass of an electron is really 1/1840th of the mass of a proton. So it's not statistically significant, right, if you look at significant digits. Right? So its mass is, and it's -1 as far as what it does to protons. Right? Or what it does to neutrons is probably more correct. So if we look at this, so 90 is equal to 91 plus a -1, right? And 234 minus 0 is still 234, okay? So let me give you another example. Let's say that we have polonium, so we'll go Pu, and then polonium is 244 and 94, right? So if this emits a beta particle, right? So beta, 0, -1, right? Or you could use an E, right? Plus, then we just have to set 0, right? 244 minus 0, right? Or plus 0 is equal to 244, right? And then 95, right, plus a -1 is equal to 94, right? And that's the way we get at that. So the interesting thing is that the place where this beta came from, so remember, we don't have electrons in the nucleus, so this is essentially what's happening. So if I have, let's make this really simple. So if I have helium, right? And helium has 2 protons and 2 neutrons. If helium was just to release beta emission, what would be left now? The mass would still be the same because I've got 4 AMUs here, and I've got 4 AMUs here, but you'll see that my proton number went up 1. So this one has 2 protons and 2 neutrons. Now this one has 3 protons and 1 neutron, because that beta emission came from the splitting apart of a neutron. That's where it came from. All right, so we can have gamma ray production. Now, remember, gamma ray is when we look at the electromagnetic radiation scale, gamma is the most energetic. So we have X-ray and then gamma. So a gamma ray is a high energy photon. Right, so it's a high energy photon. And you'll notice it has 0 mass, and it has 0 effect on the nucleus as far as mass goes, right? So it usually accompanies other forms of radiation. So you see that here I have an alpha, right? And then here I have a gamma, right? So I have an alpha and a gamma, right? So if I said this, let me give you an example of something here, right? If I said uranium, So if I had uranium 92, right, 238, that should be 2 there, my pen didn't read. So uranium 238, right, undergoes alpha, beta, and gamma radiation. So let's see how we would do that. So you would start with uranium 238, 92. When we draw this, we have helium, that's our alpha, that's our beta, that's our gamma, and plus what's left, right? So 2 minus 1 is 1. So if I have 91 plus 1 is equal to 92, let's go to the top, right? 238, 234 plus 0 plus 0 plus 4 is equal to 238. And I come over here and I look for what 91 is, right? And I get protactinium, not Pennsylvania, right? And that's what we do it, because 91 minus 1 plus 2 is equal to 92, right? So make sure all your numbers in your products and all your numbers in your reactants equal each other. All right. Did I forget something? Oh, we have what's called a positron. Here's a positron. So a positron is a positively charged particle, and it's roughly the size of an electron, right? So we give it that E just like an electron, but if it's not negative in charge, it's a positron. So if we think about the two of them next to each other, so I have this, oops, right? So this would be a positron, and this would be beta, right? So that's, sometimes a positron is called beta positive emission, right? And then this electron here is called beta negative emission, right? And we'll get to that as well. But a positron, so if we think about it, right? So if we have our helium, again, I'm using helium because it's small. So if I get this particle right here, and it leaves, right, then what I'll have is this causes the cancellation of one proton, right? So where I started out with 2 protons and 2 neutrons, now I would get, so I start out with 2 protons and 2 neutrons. At the end I get 1 proton and 3 neutrons. Okay, because the 2 of those together will act as 1 neutron. All right? So what we talked about so far was emission. This turned capture. If I get my pen to work. So this term capture means absorbed by the nucleus. All right, so capture means absorbed by the nucleus. All right. So I could ask you something like this. So we could have a positron capture by americium 243 followed by alpha and gamma emission. So if I did this, so I have AM 243, and then we have, I'm trying to find it here, 95. And it's got a capture, so capture is always in the reactant side. So it's a positron. So I release a helium plus a gamma plus something else. All right, so if you look at this in my reactants, now I have 96 total. So this would have to be 94 to get me to 96. And I have 243, 239 plus 4 is going to be 243. And if I look over to 94, that's polonium, or plutonium. Okay, so that's the way I would do that. All right, so which of the following produces a beta particle? Right, so if you look at this, right, this is just a concept check. So a beta particle produces is emission, right? So it's not this one, because this would be capture, right? So since that's capture, it doesn't work. This one right here is a positron, right? So again, that doesn't work. In C, there is no beta particle, right? And in D, right, we have an actual beta particle, right? So nuclear stability, you can read over these. Too many neutrons, right? I might want to make a neutron into a proton so you can have beta emission. So make sure you know which way the protons go. So if I have beta emission, the protons go up, but the mass stays the same. So if I have too many protons in relation to neutrons, I need more neutrons for stability, right? I might get positron emission. I could get neutron emission as well, but positron emission, the mass or the proton number will go down while the mass stays the same. Right? Don't worry about the neutrinos and the antineutrinos. That just describes what happens to the relative number of neutrons. Right? Too many protons, we could have electron capture as well. Some things you should probably read through. So a little bit on the application.